Hi guys, I'm back for part two. We left off on a condensing problem, so since these bases all have the same, since, pardon me, since these logs all have the same base, I can condense them. And there's no variables here, so I'm gonna be able to do this one numerically, so I'm gonna start with this right here. So I'm gonna put this 4 with my power property. So this becomes log base 2 of 36 minus log base 2, 3 to the 4th is 81, plus, I'm going to bring that up there, log base 2 of 6 squared is 36. So now to condense two logs that are being subtracted, you divide. So that becomes log base 2 of 36 over 81 plus log base 2 of 36. And to condense two logs that are being added, I can multiply these two things. So that becomes log base 2 of 36 over 81 times 36. So now I'm going to go ahead and clean this up. I'm going to do 36 times 36 and then divide that by 81. That becomes 16. So this is all just log base 2 of 16, which I can evaluate mentally. 2 to the what power is 16? This whole thing simplifies to 4. All right, letter B. I'm going to do my power property. These are exponents, so this is log. This is base 10. And so that's gonna, I'll just imagine that's up there. So that's 4 times 5, there's 20 x's and 5 y's minus log, if I put the 3 there, that becomes x to the third, y to the sixth. I can condense two logs that are being subtracted by division. So now I have x to the 20th, y to the fifth, all over x to the third, y to the sixth. I'm going to clean up my exponents. There's 17 more x's on top and one more x on the bottom. All right, letter C. I can condense two logs that are being added by multiplication. So the natural log of x squared minus 8 times 4 minus the natural log of x to the fifth. I can condense two logs with the same base that are being subtracted by division. I'm going to go ahead and distribute that. So that's the natural log of 4x squared minus 32 all over x to the fifth. You can't clean those up because, yeah, it's not factored, right? And even if it is factored, it's not a common factor. All right, 12. Now we're on to solving. These are a little bit more complicated than the ones before. So here we've got 4 to the third equals x squared. 4 to the third is x squared, 64. And to undo square root. So what number could I square to make 64? It could be positive or negative 8. In this case, a negative is okay because I'm squaring it, and it will become positive 64. All right, letter B. This problem has two natural logs in it. So in order to solve this, I'm going to need to somehow get these on the same side so I can condense them. So I'm going to subtract this one over here. And if you can imagine, I'm going to have two logs with the same base, with the base e, that are being subtracted. So I can condense those by division. So this is the natural log of 3x plus 4 all over 2x plus 1 equals 5. This is an exponential, or excuse me, this is a log, so I'm going to change it to an exponential. So the base here, right, natural log, that's base e. So e to the fifth is all of this. E to the fifth is 3x plus 4 over 2x plus 1. I do this on my calculator. Second ln to the fifth. So 148.41. 148.41 equals 3x plus 4, 2x plus 1 is a rational equation. I'm going to clear the denominator. I want to get that off the bottom. I'm going to multiply this side by it to make it go away. Whatever I do to one side, I do to the other. So now I'm going to have to distribute that that out. So 148.41 times 2. So this becomes 296.82x plus 1 times that is just 148.41 equals, I still have 3x plus 4. This is a linear equation. I'm going to get my x's on one side, so I'm going to subtract 3x over here, and then I'm going to subtract that over there. So this becomes 293.82x equals negative 144.41. Then I would divide both sides by the 293. So negative 144, whoops, negative 144.41 divided by 293.82, about negative 0.491. And again, on the test, check your answers. And today, I mean, I've checked these and I'm just trying to save time, but you would take that answer, you could put it in here and put it in here and make sure both sides of these equations equal the same thing. All right, moving on. All right, again, I see 2 logs in this problem, which means I'm going to have to condense before I can solve. 2 logs with the same base that are being added can be condensed by multiplication. 4 equals log base 3, x plus 2 times x minus 1. Now the log expression is alone, so 3 to the 4th equals all that. 3 to the 4th equals x plus 2 times x minus 1. And now, this is 81. And then I could do a box or foil, however you do it. And this is a quadratic. I've got to get everything on one side. So I'm going to subtract 81. So this is x squared plus x minus 83 equals 0. I'm trying this problem, I'm solving this. I have to say what x can equal to make this true. I could try to factor it, doesn't look hopeful. I'm going to do the quadratic formula. X equals negative b plus or minus b squared minus 4 times a times c all over 2a becomes minus 2. I'm going to just type this in my calculator. 1 squared minus 4 times a times c all over 2, and then I'm going to type it in to get my 2 answers. I have negative 1 plus the square root of 333 divided by 2, so 8.62. Then I have negative 1 minus the square root of 333 divided by 2, negative 9.62. And with these problems, when quadratics occur with logarithms, oftentimes there's going to be an extraneous solution, so we need to check. We need to make sure that the argument right here, the log base 3 of whatever is here, can never be negative. So if I put 8.62 in there, that's going to be 10.62. That's going to be okay. And if I put 8.62 there, that's going to be 7.62. So this one works. Let's put this. If I put a negative 9.62 in there, that's going to create a negative. And I mean, you could even try it. If you go math out the math, and you do log base 3 of negative 9.62 plus 2, and just hit enter just on that part. It's non-real. It doesn't exist. Okay, so this is an extraneous solution. Make sure you cross that one out. Okay, now we're on to modeling with exponential growth and decay functions. So this is your format for exponential growth and decay. A is the initial value, which they're saying is 12. And then I'm supposed to figure out what the growth or decay rate is. Well, they tell me that at 5, the output's 3.93. Well, this is X and this is Y. So you're going to plug this in. You're going to take this, put it right here, and you're going to put the 5 and put it right there. So you have 3.93 is 12 times I don't know to the 5th power. Trying to figure out what the growth rate is. So I'm going to divide both sides by 12. 3.93 divided by 12, 0.3275. And then that's some number to the 5th power. You don't do the log of this. The exponent's not unknown, right? It's the 5th power. How do I undo 5th power? 5th root. Whenever I do to one side, I do to the other. So the 5th root undoes the 5th power. So now I have b, and then I got to do this. On your calculator, it's math, and it's the 5th one. Remember, if you don't have a graphing calculator at home, there is the Calculate 84 app for free. It's a carbon copy of this calculator. I'm taking the 5th root of 0.3275. So, I mean, basically 0.8. I mean, I could carry it out. 1, 2, 3. So now it wants me to write the final rule. So the rule is the initial amount. So this problem is decay. And then on the test, I'd make sure, like, put the 5 in there and make sure it spits out 3.93. 12 times 0.7999 to the 5th. Yep, 3.9. It's not perfect to be rounded, but it's very close. Consider the exponential function defined by 25 times 0.631 to the t. State whether this involves growth or decay. State the constant percentage rate of increase or decrease. If the base is between 0 and 1, it's decay. Right? And it's not that. 1 minus something made 0.631. Right? So you're going to go backwards. You're going to do 1 minus 0.631 and figure out what that rate was. So 1 minus 0.631, 0.369. So that converted to a decimal is 36.9%. So whatever this was, it was losing 36.9% because it's retaining 63.1. So exponential decay by 36.9%. Same thing here, new problem, growth or decay, and what's the constant percentage. So if the number in here is greater than 1, it's growth. This is greater than 1, this is growth. This time 1 plus something made 3.7, right? So maybe you could do that mentally, or maybe you could do that, take away 1, right? The rate is 2.7. That's as a decimal, right? So you got to move it over 2 places, boom, boom. That's actually a growth of 270%, right? So this is a growth of 270%. 16. Another one, write a formula for an exponential function whose initial value is 28, which decreases at a percentage of 4.3. So it's initial amount times 1 minus, because it's decreasing. I'm going to switch 4.3% to a decimal. That's 2 places to the left, or divide by 100. To the, put X or T, and then I'll clean that up. My calculator, I mean, you could leave it like that, it's fine. Oops, didn't like that. Didn't like that parenthesis I put in. So 0.957 to the T. Suppose a certain town has a population of 67,000 and at the beginning of the year 2004, and the population increases at a constant percentage of 1.59%. So I know I'm going to need to switch this. So that's what I'm going to add to 1, right? 1 plus the rate. So here we go. Y equals initial amount times 1 plus that to the t or x. According to the formula, when will the population be 100,000? They're giving me the output, the y value. I'm going to put that right there. 100,000 equals 67,000 times 1.0159 to the t. This is an exponential. What undoes an exponential? A log. After you get the exponential expression alone, the base needs to be alone. So I've got to get rid of this. Cross out your zeros there. 1.493 approximately equals 1.0159 to the t. Okay, now we're ready to change it to a log. The log, that's the base, 1.0159 of 1.493 is the answer. And I'm on the calculator, math alpha math, 1.0159, 1.493. Calculator's got this stored in there. About 25.4 years. According to the formula, what was the population of the town at the beginning of 2011? Well, this problem started in 2004, so that's been 7 years. They're giving me the x. So no solving here, just plugging in and going straight to my calculator. Putting a 7 in there. 67,000 times 1.0159 to the 7 years later, 74,822. Approximately 74,822. What is the doubling time? So there's a couple of ways to do this. The easiest way is, you can double this and put it over here, but when you divide that by the double, you're just going to get 2. So you can just go straight to this. Now, it doesn't matter what two numbers are there. I want to know with this rate, how long does it take to double? So I'm going to go straight to a log. $1.0159 about 43.94 years. And you could check, you should make sure, right? Like, so if you go 67,000 times 1.0159 to the 43.94, 67, let's double. 67,000 times 2. Yep. Okay. Almost done. Suppose a half-life, now this is the problem, if they give you the half-life, you can use the half-life formula, right? So they're telling you the half-life of some radioactive substance is 2.7 seconds, and the initial amount was 84. Write a formula. So the formula is y equals the initial amount times, this is a half-life problem, time divided by the half-life. How much of the substance is left after 4 seconds? This is time. They're giving you t. No solving here, straight to a calculator. 84 times 1/2 to the 4 divided by 2.7. So 30.08 grams. 30.08 grams. After how many seconds will there be 1 gram remaining? So now they're giving me the answer. So 1 equals, I want to know when the output's 1. So this is an exponential. I'm going to convert it to a log, but I need to get that alone. I'm going to divide both sides by 84. .0119. 0.0119. And by the way, you could just leave it like that and type in, when you go to the log, just use a fraction. So this would be the log of base of 1/2 .0119 is t over 2.7. Type that on my calculator. 0.5, 0.0119, 6.393, 6.393. Trying to get t alone, it's being divided by 2.7, so I'm going to multiply by 2.7. In about 17.26 seconds. At what percentage rate is the amount of the substance decreasing per second? So I know it started with 84, so I'm going to find 1 second later and then divide those two and find how much it changed. I'm going to do 1 second for my time. I'm going to go 84 times 1/2 to the 1 over 2.7. Type that into my calculator. So after 1 second, there's 64.98 left. So now I'm going to take, right, here I am on 1 second divided by how much was there to start with. So now that's not how much it's losing. That's how much is left. So I got to do rule. Sorry, it's kind of hard to see that. Oh, right? Oh, it's this one. So I'm going to do 1 minus that. 1 minus that. So it's 0.2264. So that's about 22.64% losing per second. Okay, well, I hope that helped, and I'll see you soon. Bye.